original room. It's a great pleasure to have Oliver Gressel with us this morning / evening. It's really nice to be able to take advantage of the pandemic in at least one positive way and get some international voices into the TAP Colloquium series. So Oliver has sort of done some circulation in his time in academia. He did a master's degree in Tübingen, his postgraduate research at the IAP. Then he spent some time in Potsdam and Queen Mary University, Nordita, and is now back at the Institute for Astrophysics in Potsdam, where he's on the faculty. Oliver does a wide variety of really exciting numerical astrophysics related to disks and MHD. And I understand that he's gonna tell us a little bit about dynamos and turbulence today. So take it away. And as I said to many of you, probably heard this before we officially started, if you have a question during the talk, please feel free to put it in the chat window, and I will try to keep an eye on that, and we'll take breaks every once in a while just to make sure that everybody's on the same page. So please don't hesitate to put a question there so that we can stop and try to preserve some of the interactivity that has been a hallmark of this colloquium series. And then at the end, we'll have an open time for questions. And I'll just make one more quick advertisement, which is that I believe Oliver has made himself available for meetings throughout the rest of the week around this same time. So a link was sent out to all of TAP. So if you're interested in chatting with him further, please consider signing up for a time. All right, take it away. Thanks.
Thank you for the introduction, Caitlin. And I do really like this feature that you also try to recreate this aspect of a seminar or colloquium, that you actually interact with the people. So I'm really looking forward to chat to you, of some of you guys in smaller groups. So today I'm gonna talk about dynamo theory. So this is a theory concerned with the amplification of magnetic fields in various objects. And as Caitlin mentioned, I guess the thread through my quite diverse career is that it was mostly concerned with disks. So here we're looking at disk galaxies, and they are a prime example for an astrophysical dynamo, and they're actually the only object where we can really look inside. So we see these in the radio continuum, and so this is a bit like X-ray. So we can really see through these things, and we can really map the magnetic fields. And this talk is going to be concerned with trying to find an effective theory, a mean field model. And it's in the honor and in memory of Karl-Heinz Redler, who was one of the founding fathers of this mathematical framework, who passed away this February. Okay, so to get started, here's a beautiful Hubble image of a nearby spiral galaxy, Whirlpool galaxy M51, and you can see there's a lot going on. You have the grand design spiral arms. You do have, you see the active star formation going on, and so this is a very dynamical system. There's some nearby companion. There's some signs of interaction. What I always find amazing is that this galaxy has a large-scale ordered magnetic field that we see in the polarized synchrotron emission. So these are the polarization vectors in the radio band rotated by 90 degrees. So now they would trace the magnetic field lines. And you might say, okay, that's pretty trivial. You have a differentially rotating galaxy. You have some background field stemming, from the formation of the galaxy. It gets dragged in and amplified, and then it gets wound up by the differential rotation. And that's that. But it turns out if it only were that, then those fields should largely follow the azimuthal direction, because then the pitch angle of the magnetic field lines would be vanishingly small. Yet we do observe significant pitch angles of the magnetic field direction with respect to the spiral arms. And this means that there has to be a mechanism that maintains a radial magnetic field as well. So a field going in out from the center, for example. If you account for the turbulence that you typically have in the interstellar medium, orders of magnitude of tens of kilometers per second, you can estimate a diffusion coefficient. And we know magnetic fields, the induction equation, are subject to diffusion. You couldn't actually maintain these radial fields over the lifetime of the galaxy were they just a primordial field. So you need some active mechanism to reinforce these beautiful large-scale ordered fields. And that's what's called a mean field or large-scale dynamo. So unlike a small-scale dynamo, this effect can really create a flux, whereas a small-scale dynamo can only amplify the RMS magnetic field. So to get this system scale, large-scale fields, something that is ordered on scales larger than the turbulent eddies, you need some mean effect. And a typical example for that is this beautiful loop here from the alpha effect. So whenever you have a helical flow, something that stretches the field out and then twirls up the little loop that's created, that will create a current that's parallel to the field. And that's something that you don't naturally get in the induction equation. So this is something that can, you see, couple toroidal and poloidal field, for example. And that's the idea that Parker had for the solar dynamo in the sun. And so this helical alpha effect can easily be envisioned as being created actually by the expanding motion of supernova remnants. And I have a little animation that I made during my time at Nordita for some outreach. You see a single supernova remnant expanding into the ambient interstellar medium. There are some field lines illustrated for visualization purposes. And you can see that while the remnant expands, it will actually spin up. And that's due to the effect of the Coriolis force. So the equator, it expands faster. This will spin up the most from the omega cross V force. And the mutual orientation of the expansion and the rotation is such that you have a positive helicity on the top half and a negative helicity on the bottom half of the remnant. You can see this by the way the field lines are twirled up on both ends. So this will produce you an alpha effect of one sign on the top and of the opposite sign on the bottom of the remnant. Now, if you think of the medium in the galaxy being a superposition of single supernova explosions, then you pretty quickly arrive at the result that the net alpha effect is 0 because the parts from the bottom half and the top half of the remnants, they will on average cancel out. So this simple thing will not work. So you need to find a way to break the homogeneity of the turbulence. So we've already broken the isotropy of the turbulence by introducing rotation. Now we can see that if the location at which the supernova remnant sets off is slightly offset from the galactic midplane, then instead of becoming spherical or peanut shaped, it will actually become pear shaped. So the part of the remnant that expands into the lower pressure ambient medium high above the disk, it will expand at a higher velocity because there's less opposing pressure on the outside of the remnant. So this means that the further the remnant is set off, this further supernova explosion is set off from the midplane, the more asymmetric this effect will become. And this means that then this remnant on the right-hand side, for example, it will have a stronger alpha effect on the top half than that on the bottom half. And now if you do a convolution in the vertical direction with an assumed vertical distribution of stars or supernova explosions, then you can actually show that you get a non-vanishing alpha effect for this configuration. And that was really the insight that we came to when we did the simulations during my PhD now over 10 years ago. So this is just to illustrate the type of direct numerical simulation that we performed. This is a local slab of a disk galaxy. This is 1 kiloparsec across here. It's typically a few kiloparsec up, and you can see here the density, the thermal pressure, the temperature, and on the right-hand side, the magnetic field strength. And you can see that there's a high Mach number turbulence ensuing. And you can see this effect that the remnants that break out of the galactic midplane, they arrive at a larger radii. And so we were able to actually diagnose then this alpha effect in these simulations. And this is what this talk is about today. And we found actually that our theoretical work on measuring these mean field coefficients could nicely explain the overall field amplification that we actually found in the DNS. So we did actually produce a working dynamo in these simulations. So this slide is
Great.
to actually
Hi,
show.
Oliver.
Yes.
Can I, sorry, maybe I'm not interrupting in the correct way, Caitlin said, but in the movies you were just showing, is the way to tell that it's high Mach number turbulence, is that just from the density contrast?
Okay, yeah, you probably couldn't see that just by eye. You probably would have to actually, yeah. You can see it's shocks mostly. So it's actually, it doesn't really have the aspect of Kolmogorov cascade. You probably have a lot of nonlinear dissipation and then non-local effects in K-space. And that's something that should also be studied. All right, so this slide is just to illustrate the ideas for adopting a mean field approach. So the blue is the large-scale magnetic field lines, and the red is some supernova explosions. This is actually from a DNS that did a whole galaxy, but the argument is you cannot really afford to resolve the relevant scales of the turbulent eddies in global simulations. So really have to do a dual approach where you start from doing local box simulations. So we typically put these kiloparsec scale boxes at various locations in the disk, sampling properties throughout the galaxy. But then we actually want to use this DNS to derive a closure, a mean field model that we then put into a large scale global dynamo simulations. And we did that actually in 2013. So the framework that we're going to adopt is called mean field dynamo theory. And we will derive an induction equation for the mean field, where we consider that the velocity can be decomposed into a large-scale ordered, slowly varying mean velocity and some residual fluctuations. And the same can be done for the magnetic field, that we can split into a large-scale mean, a smooth mean, and a small-scale fluctuations. And then we can derive an induction equation that tells us about the evolution of the mean field. And so the time change of the mean field is just the U cross B, curl U cross B, as for the actual induction equation. And then we get an additional term, which is called the turbulent electromotive force, which subsumes correlations between the small scale velocities and the small scale magnetic fluctuations that contributes to this induction equation whenever there's a non-vanishing mean. So as soon as we have a turbulence that's not fully isotropic, that's not fully homogeneous, this will produce a non-vanishing mean that then determines the evolution of the large-scale fields. In particular, if you can find a mean field that is actually proportional or linear in the mean fields, then we can show that this linear feedback here will create an exponentially growing mean field. And that's really the power of the mean field formalism. There's also a diffusive part, obviously, with the turbulent diffusion here. But you can argue that when you go to large enough scales, so the system scales, the integral scales of the galaxy, then this term will become progressively smaller compared to this one, which remains constant with scale. And then you can always find a scale where these mean field effects really do play a role. Just a quick aside for everyone that's not an expert on MHD or the induction equation, this curl U cross B term might seem a little opaque. So I've actually here broken it down so that if you do use this vector identity, you can break it down into 4 terms. The first one vanishes by the virtue of the divergence B being 0 identically from the Maxwell equations. And then we're left with 3 terms. So the first one, this is related to divergence U, and with a minus sign. So this means if you have a negative divergence, so converging flows, then that means the magnetic field gets compressed. So this can amplify the field. In the contrary, if you have an expanding flow, then this will dilute the magnetic field. So magnetic field lines are like frozen into the fluid. So this will also mean, for example, that in the shock front, the magnetic field will be compressed and amplified, and so on. The next term is a B dot grad U. So whenever the velocity has a shear in it that is perpendicular to the magnetic field, then you do actually stretch out the field lines. So this way you can actually do work onto the magnetic field by having motions, turbulent motions. So the last term is simply the advection term. So u dot grad, that means a directional derivative along the velocity. So whenever the magnetic field changes along the velocity, then these changes will be transported along with the flow. So this just means that the magnetic flux is frozen into the fluid. And in that way, we can understand the induction equation that tells us about the evolution of the magnetic field. All right, so we want to derive this mean field induction equation, and that's pretty straightforward if you introduce a handful of properties of your averaging. So I already mentioned this can be large scale versus small scale. This can be mean versus fluctuating. In the idealized sense, you would like to work with ensemble averages. When you do direct simulations, that's of course not possible. So you have to find some sort of a spatial mean, for example. What we do is we average in horizontal planes of our boxes, and then we consider everything to be a profile of the vertical direction, because that's where the interesting properties are. That's where the galaxy is stratified. That's where the rotation vector points, right? So this is the direction of interest, whereas we assume everything in a horizontal direction is homogeneous. So we need to make sure this, if we apply an average to an average, this doesn't change the average. That's trivial for geometric averages, but this actually already precludes some sort of filtering approach where you do spectral filtering, for example, that would violate this. Means of fluctuations have to be 0. And this has to be linear, so you can pull it out of sums. It has to be commuting with the differential operators you want to use. And these properties then actually mean that mixed terms, by virtue of pulling the mean out of the average, you can actually show that then, because this is 0, then mixed terms have to become 0. So if we now write down the induction equation and we split the magnetic field into mean and fluctuation, we split the velocity mean and fluctuation, and we compute the 4 terms multiplying out this expression, and then we take averages of the entire thing, then we can arrive at the mean field induction equation. So you see the fluctuations here, they disappear. We are left with the time evolution of the mean field. And on the right-hand side, we get the curl U mean cross B mean. That's from these 2 terms. The mixed terms, they drop out. And then we have the fluctuations that are then averaged. They are subsumed in this mean turbulent electromotive force. And now we actually want to make progress by modeling this mean electromotive force in terms of the mean fields and in some statistical sense on the properties of the turbulence. And one approach is to have this parametrization that the turbulent electromotive force is linear in the magnetic field and its gradient. So you can think of this as a Taylor expansion, if you like. But there's also a more intuitive way actually to motivate this. So if we want to find the mean electromotive force by doing a time evolution of its constituent parts, then we can take the approach that we say, okay, the velocity fluctuations, they may be given. This is the turbulence by our supernova explosions. And that's a fact even in the absence of magnetic fields. So this is what's called kinetic driving or the kinematic limit. You could imagine that you have a second part when you have magnetic fluctuations that pre-exist without mean magnetic fields being present, that you have when you have magnetic instability. So that we exclude for the time being. So if you take our velocity as given, then you only have to actually find a time estimate, time evolution for the magnetic fluctuations. So we need to figure out how the magnetic fluctuations evolve in time, and then we can estimate our turbulent electromotive force. So we want to derive an evolution equation for our magnetic fluctuations. And we do that by, again, writing down our induction equation. So note that unlike in the previous slide, we don't have the overbars here. So this is not an average equation, but this is just the induction equation written in a clumsy way by splitting all these terms again into the means and fluctuations.
Oliver, before you go, can I have a quick question? You were looking at
Yes.
your ad hoc parameterization. What was, did you say what the alpha was?
The alpha is a tensor that we need to specify. So this encapsulates properties of the turbulence that stem from the rotation of the galaxy, from the vertical stratification. So this is whenever the symmetry of the turbulence is broken, then this will be a non-vanishing term.
Okay.
So this is in a way the unknown that we want to determine. That will encapsulate our subgrid model, our small scale physics.
Okay, thanks.
Okay, so on the previous slide, we had the mean induction equation.
Or a function of height, or a function of height and time?
We'll come to that. So it can be a function of position and time, and it will also be a function of space, spatial dimension. So it turns out it's actually a non-local, non-instantaneous relation. Okay, so we'll just subtract our mean induction equation from the total one. Here we actually have all 4 terms, so there are 2 mixed terms. And if we subtract this mean equation, then we arrive at a evolution equation for our fluctuations. And you can see there are 4 U cross B-like terms on the right-hand side, plus the dissipative term. So I'll quickly go through a short characterization of these terms. So this first one is just the mean flow and the small scale fluctuations. So this is then just how the fluctuations get advected with the mean flow, how the fluctuations get sheared out by the mean flow, how the fluctuations get amplified if there's a converging mean flow, and so on. This is important in the galaxy because there is an ordered mean flow that is the background rotation. So this will actually stretch out the fluctuations, make them anisotropic to some degree. The next one is just the cross product of the fluctuations without the overbar. That is actually what makes the small scale dynamo. So this means if there's a turbulent random small scale velocity that acts on the fluctuations, it will amplify these fluctuations in a way. And this can be, if it's sufficiently chaotic, it can also be a small scale dynamo. The next one is the mean electromotive force appearing here with a minus sign. So this shows that this is actually, if you do a B dot into this equation, you can show that this will actually transfer energy from the small scales to the large scales and vice versa. So this is really the term that puts energy into the large scales. But the really exciting term in my eyes is this last one. So this means if you have a turbulent velocity, this will actually tangle up the large scale magnetic field. And this will create magnetic fluctuations that are correlated with the large scale magnetic field by definition, right? So the change of the fluctuations here is the velocity fluctuations times the large scale field, which is relatively smoothly varying in space and time, which means that it's approximately constant. And so it means actually, if you now plug this fluctuation back in here, we'll actually get 3rd order correlations from these, and that's why they're usually actually ignored. But we will get a 3rd order correlation with this one, and we can pull the mean B out of the average, and then we can see that we actually have an EMF that is linear in the B field. And if you actually massage this integral a bit, you can show that this will actually end up something looking like the kinetic helicity, so the vorticity times the velocity. And so whenever you have a helical flow, there will be a non-trivial electromotive force. Okay, so there was already the question.
Okay. I can ask a question on the previous slide?
Sure, sure.
So on the previous, yeah. So I'm not very clear with the term, looking at the equation, the 3rd term, so the average of the cross product U cross B. So you said that this term is the one governing the transfer of energy from smaller to larger scale and vice versa. But looking at also the equation above, seems that you added and subtracted the same term. So is that the term, so I don't understand if you, since it looks, it's only a mathematical term which you added, is the origin of the energy transfer due also to other term, or it looks just as a mathematical artifact, the way it's the 2 equations are written? Can you clarify this?
Okay, so I was just referring to that this term actually shows up both in the induction equation for the mean fields with a plus sign, and it shows up in the induction equation for the fluctuations with the minus sign. So this is just hand waving at this point. I mean, you could do the b dot b here and the lowercase b dot b here. And then you could, if you assume that this has one sign, then you could say that this will really, you know, link the means to the fluctuations in a systematic sense. So this is in a way like a, you know, a diode. This will, well, maybe that's, yeah. But so this was just, yeah, man, there's a brief discussion of these 4 terms that show up here, because this can easily, you know, become obviously this is, yeah, this is a very quick way to go through these equations.
So in other terms, yeah, so in other terms, there is the only term which gives the energy transfer intrascale, or is the dominant term? So if you haven't added this term, would you have energy transfer between scales or not?
That's actually a good point. I suppose that this would create some energy transfer as well, if you would then say this is a large scale flow that, so this is actually something that probably would deserve a lot more scrutiny. And there's this idea connected to the alpha effect actually that's called the inverse cascade. So the idea is that you actually progressively build up energy from smaller scales to larger scales. I often like to think about it as, because these means don't have to be related to scale at all. They could just be temporal means or ensemble means. So I'd like to interpret the alpha effect more like something that gives a systematic effect on large enough scales, like for example system scales, so that it's even a non-linear term in the K space, that it connects the scale of the turbulent eddies with the scale of the system as a whole directly, in a sense. And it does so by this virtue of these correlations giving a contribution when you average over them. So, but there's certainly a lot of interesting questions you can do, for example, a scale by scale model. People like Eric Blackman in Rochester have attempted that, where we really try to do this in Fourier space. I'm rather naive in that sense, and I like to think of the means and the fluctuations, and not think so much about the spectral realm with regards to that. I hope that answered your question, and maybe we can come back to that at the end.
Yeah, maybe ask too early, so maybe we can come back later. Okay, thanks.
All right, thanks. Okay, so this is diving really deep, just to give a motivation actually why you can believe that there is a mean electromotive force. It's a linear function of the magnetic field, and a motivation for that. So the question was raised what this alpha depends on, and in our previous work it would depend on the vertical position in the disk and on time, even though typically it would be steady state in time, and then we only would plot vertical profiles, and I'll come to that, and you'll see that this is what we obtain there. And the first generalization I would like to make is to actually introduce a non-local generalization, where now alpha is not just a scalar. So it turns actually out from symmetry consideration, it's a pseudo-scalar. So it will actually change sign if you change the sign of a constituents. But it's not a scalar function linking the mean field and the mean EMF at any given point on time and space. So it's not an instantaneous and local thing, but it can be non-local in the form that the alpha effect is a convolution kernel now. And so the mean EMF at any given location Z, it will be an integral over the vicinity of the mean fields at Z minus some integration parameter theta. And so this alpha will encapsulate the non-local effect of the eddies, right? So if there's a turbulent eddy stretching out the mean magnetic field, And this will happen over a characteristic time scale, and there will be a characteristic length scale to this. So the linking between the imposed perturbation, the mean field, and the response of the system producing this mean electromotive force will be a non-local one. And so this convolution kernel that can then be expressed in Fourier space as a spectral amplitude. So each Fourier mode in the mean field will be linked to the Fourier mode in the electromotive force via an alpha effect that is now a function of scale. And the same holds for the eta tensor, which is representing turbulent diffusion. So eddy diffusion will be a function of scale here as well. And an ad hoc model for the kernel has been found to be, there's a good representation taking a Lorentzian shape, where you have an amplitude, and then this 1 plus some wave number squared. And so you see there's a characteristic wave number. And when you put this back into real space, you can actually see that the alpha will be an exponential in displacement. So as you go further away, the points taken in the integral will exponentially decay away in the way they contribute to the electromotive force at a given point in space. And that makes a lot of sense if you think about turbulence being a intrinsically non-local effect, but something that's sort of Galilean invariant.
Hi, Oliver?
Yes.
Sorry to interrupt. Just a question about this slide. The fact that here the dependence is only on the vertical wave number is just to make the point, or is indeed the assumption, the underlying assumption here? Because in the simulations that you show, the turbulence is seems to be like 2D or 3D. At least it was a real wave number there as well.
That's true, yes. So because we take the average in the horizontal direction, there's no information kept on these dependencies. So we assume that everything is homogeneous, that, for example, the way the galactic rotation curve changes will not significantly change over the radial extent of our box. So that way, all the closure parameters will only be functions of the vertical coordinate, and partly for simplicity, and partly because we assume that everything is homogeneous in the horizontal plane. This is sort of the one-dimensional way to look at this, that we have integral kernels in the vertical direction. The general case would probably quickly become untractable because you need quite a bit of statistics. So you need a statistical foundation for your averages, otherwise you'll end up with large fluctuations. Okay, so it turns out that, yes, the Lorentzian shape is a good approximation to the kernels that we find in the spectrum, and that translates to an exponential decay in real space with displacement, which is actually really nice in terms of the intuitive understanding. So the same thing actually counts for the time dependence of the effects. So we can think of mean fields that vary in time. For example, the sun has a solar cycle of 11 years. That's admittedly long compared to the eddy turnover time in the sun. But there might actually be situations where you have oscillating solutions to dynamos. And there the question arises, what now happens if these mean fields vary in time? And that means that the mean electromotive force might not be an instantaneous result of having a mean field, but it will be integral in time, where now the alpha effect is a convolution kernel in time. And so it relates the mean field at a certain time and a certain displacement in time to the EMF at the time of interest. So this means that we integrate over the turbulence in time. So the turbulent eddies, they will take some time to stretch out the field, to twirl up the field. And this is reflected in a sort of a time lag between the cause, the mean field being present, and then the mean electromotive force building up as a response, as a result of this inhomogeneity. So this is really at the heart of this formalism, is that you actually need a mean field to create enough fluctuations that are correlated with the velocities to produce a net effect, and that this is linear in the mean field. Okay, and again, we can actually take this to the spectral realm. So if we measure our alpha effect as a function of oscillation frequency of the mean fields, then we can also measure a kernel shape. And this model here has been put forward is a oscillation with a decay. So obviously on long times, everything will become uncorrelated. So you have an exponential envelope. But on short times, actually the rotation of the eddies and the rotation of the galaxy, it can actually be reflected in time lag phenomena and in even phase shifts in terms. So this can actually become a imaginary part as well. Okay, so how do we measure these things? And so the spectral representation of these kernels actually makes it very straightforward to infer these spectral amplitudes by means of what's called the test field method. So early on, people would try to actually relate the electromotive force, which is something you can compute in DNS, to the mean field, which is something you can compute in DNS. It turns out you have 8 tensor components in the simplest case, and you only have 2 magnetic field components and 2 electric field components in the horizontal plane. And so this problem is underdetermined. And it turns also out that if you really want to look at gradients in the mean fields, then it often comes very, very difficult to actually determine what of this variation in the vertical direction is now a mean magnetic field gradient and what of that is just a by chance fluctuation. And so these direct inversion methods, least square approaches, SVD, PCA, they turned out to actually be very hampered by noise, and it's very difficult to actually get the eta component especially. So the solution to this came along about 15 years ago, and this is to actually introduce the inhomogeneities as superimposed fields. So for each tensor coefficient that we want to solve, we superimpose not 1, but 4 magnetic fields with a certain variation. So we have, for example, a field that varies like a cosine and points in the x direction. We have one that varies like a sine and points in the x direction. And then we have 2 fields that point in the y direction. And that means that we actually have a orthogonal basis. We have enough base vectors to actually describe our coefficients in. And that way, the inversion is actually as trivial as writing down this rotation matrix here with a spatial dependence of these mean fields. So the price for this is that we actually have to solve for each tensor coefficient, for each tensor we want to get. We have to solve this induction equation for magnetic fluctuations. So these are now magnetic fluctuations that arise as a result of the presence of a mean test field. And you can see this is sensitive to the turbulent velocity in the simulation and the mean flow, just as we've seen in the induction equation for the actual magnetic fluctuation. So these are, in a way, virtual magnetic fluctuations that are the result of a very well-defined set of inhomogeneities that we impose in addition. So in practical terms, we did actually do 7 spatial modes. So we had 28 additional induction equations to solve. And we had 11 Fourier modes in time. So we had to solve 44 induction equations on top of that. And if you're still listening, CK, it would be amazing if we could put this on GPUs, because this is essentially passive equations that we solve on top of the DNS. And this would lend itself to actually be put onto a Xeon Phi or a CUDA a GPU. So this is really putting a lot of demand. These supernova simulations are already expensive, but this is actually solving a lot of equations on top of it. But it's a beautiful, elegant scheme. So we can prescribe the fields in a way that they vary in space with a certain spatial frequency, and they oscillate in time, just as we wanted to extract the closure parameters as a function of a vertical wave number and as a function of oscillation frequency. And this gives us a very complete description of the turbulence, indeed. So this is from a test case. This is just a hydro simulation. So this method actually still works if you don't have any magnetic fields in the simulations. So we just solve the momentum equation, and then this bunch of induction equations for the test fields alongside. And here we show the amplitude of the alpha effect as a function of wave number, and you can see that it has this Lorentzian shape. So at large spatial scales, everything becomes uncorrelated. There's no mean effect. And on small scales, we approach an asymptotic value. That's the value we use to measure just by having an instantaneous local closure relation. And the same is true for the magnetic diffusivity. Okay, and we can do the same for this benchmark case and look at the frequency dependence. And we did a simultaneous fit of the real part and the imaginary part. Here you can see that the real part has a plateau for quasi-stationary fields, and it will decay away to 0 for the high frequencies. That is easy to understand, because here things become very uncorrelated. And then if you take the ensemble average, or the time average in our case, and the spatial average, then this will just average out to 0. But here in the intermediate frequencies that correspond roughly to the eddy turnover timescales, you can see that there's actually a slight peak here. That's when sort of the eddies become resonant with the oscillation, with the beat of the varying test fields. And in that regime, it's also where you get a non-negligible imaginary part. So this means that there's a significant phase lag. So the response, the turbulent electromotive force as a result of applying a mean field, has actually a significant phase lag with respect to the mean field. And this can actually have a consequence for butterfly diagram, so the way a dynamo solution oscillates. And so the same is true for the turbulent diffusion. All right, so, but now let's come actually to some results from the supernova simulations. And as I mentioned, we only consider the vertical direction, and there we have the tensor will become simplified, that it has a diagonal. That is what does the dynamo effect, and it has this off diagonal, which turns out is perfectly antisymmetric, which means if you do the curl of this EMF, this antisymmetric part will actually act like an advection. So this is called turbulent pumping. So this means that magnetic field will be expelled of regions of high turbulent intensity into regions of low turbulent intensity. And this is actually a significant effect in the galaxy, and it actually amounts to retaining the field, the horizontal field in the galactic disk, and counteract the effect of the galactic wind that actually removes the mean magnetic field. And we actually shown that this effect is the crucial ingredient to having a galactic dynamo at all. So this was really the missing piece to make sense of the galactic dynamo then 15 years ago, 10 years ago. So the diffusion tensor has a diagonal that is describing the diffusion of field. And it also has an off diagonal, and this is called the Redler effect. This is something Karl-Heinz Redler has discovered in the late 60s. And it turns out that you can actually also drive a dynamo with that couples the mean current to the mean field. And so this is how these profiles would look like when we measure them. You see the alpha is a pseudo-scalar. It's positive on the top hemisphere of the galaxy. It's negative on the other half. And these lines now actually show the scale dependence. So each of these is for a different spatial wave number of the test fields. So the dark red line is for the largest scales, and then going progressively to smaller scales. And we see the amplitude of the effect changes, diminishes amplitude. And as a big surprise, it actually turned out that the the pumping term gamma z that I just had mentioned, it actually has the opposite scale dependence. So it is actually growing when you go to smaller scales, and this would actually amount to a UV catastrophe of some sorts. This is something that has puzzled us quite a bit. We speculate that this might be related actually to the multi-phase nature of the interstellar medium. So we do actually include a quite complex cooling function. So our interstellar medium is clumpy. There's generally an outflow in the warm component, but the cold clumps, they rain down again in a galactic fountain flow. And this galactic fountain entrains part of the magnetic flux as well. So the magnetic field lines, they are anchored in these clumps and they've been dragged down again. And because the clumps are on small scales, we imagine that this might explain why the amplitude of the effect is actually seen predominantly in the small scales. So here's a vertical profile of the turbulent diffusion. You can see in the midplane where the density is high, the RMS velocity is lowest, and here the effect is smallest. And again, we see that there's a dependence on the scale, so that the amplitude is highest for the large scales, and it gradually declines as you go to smaller scales. And
can you just say what scales those are in that last? You're gonna guess well.
That we can actually see here. So here, what I did is actually these curves, they have some fluctuations. So I did filter them just to get a meaningful amplitude measurement. And then I would do at 600 parsec above the disk, I would just measure the amplitude. And if I plot that as a function of wave number, you can see we get these Lorentzian curves. And you can see this is the turnover at about 8. So that would be scales of a kiloparsec roughly. In fact, so it turns out actually that we do have scale separation of about an order of magnitude. So the turbulent eddy scale in the midplane, near the midplane, is typically, you know, the size of supernova remnants, 75 to 125 parsecs. And so it turns out that the exponential scale length on which the mean field response decays is on the length scale of these eddies. So as you would expect naively. Okay, so for the turbulent pumping, we do actually see the spectrum here. It's increasing. So we have this UV catastrophe. If you think of a flat spectrum, this would be a delta distribution in space, right? So this would be a local relation again. So this is something that we also now actually confirmed in just simple simulation of forced turbulence. But there the curves actually do turn over again for high wave numbers, as you need, because that's where your numerics becomes very dissipative, right, at the large wave numbers. So, and then here we again have the Lorentzian kernels for the turbulent diffusion. And so this will actually help us to do a very complete mean field model. And I'm working actually on putting these convolution kernels into mean field simulations as we speak, actually in the context for accretion disks, which CK might be interested in. I'll skip this slide and I'll come to the spectral dependence in the time domain. And here, as I mentioned, we had a real part and the imaginary part because there can be phase-lag effects. And again, we did smooth filter just for the purpose of determining amplitude. And we can see that here covering 3 orders of magnitude in frequencies, that around a few percent of the million-year turnover timescale, that there's a peak in the imaginary part, and then we unfortunately we didn't quite manage to resolve the plateau here in the low frequencies, because this would require long integration time to get good averages. So this is very difficult to obtain actually, but we find the overall shape of these effects here as well. Same for the pumping here, you see that actually the real part changes sign here for intermediate frequencies. So the question is, does the pumping actually reverse, or does this just mean that we have a phase lag that's larger than pi over 2. And unfortunately, that's in that sense degenerate. So we can't actually really make a conclusive statement about this here. And you can see here for the pumping, for the turbulent diffusion, we do get a somewhat broader function. So the high frequencies, turbulence can still be destructive. It can still diffuse by a random walk of field lines, whereas you need some more coherence to actually produce the alpha effect. So that actually goes to the realm of more slowly varying mean fields, so that actually the eddies overturning and producing these helical motions in the stratified medium, this takes a certain amount of time to actually make sure that you get the non-vanishing mean electromotive force. This is just plotting the normalized complex amplitude and the complex phase to illustrate that there's a growing phase lag going to higher frequencies, and that the turbulent diffusion has the envelope most to extending to high frequencies, whereas the other two effects, they actually require slowly varying fields to actually act on the fields in time to produce these correlated fluctuations. All right, and that's just a slide stating the equations of the DNS, and I haven't actually made a summary slide, so I'll stop here and I'll take questions. Thank you.
I'll do the, imagine that's the sound of more than 2 hands clapping. Thank you, thank you, Oliver.
Thanks.
So while people are thinking of their questions, I'll start asking you one. If you go back, I mean, I was thinking about this, you mentioned it on the last slide briefly, but so how long are you running the simulations? How long does it take to sort of get the sort of pseudo steady state that you're using to do some of this analysis?
So there's like 50 million years before the turbulence is steady state, and then we typically integrate a couple of 100 million years to get enough statistics to drive down the error bars. So these are moderately expensive simulations. So the resolution is not terribly high. We have I think six parsec is the diameter of a grid cell. So in
terms of that's just like a handful of rotation periods then.
That's right. We tweaked one parameter. We have a rotation frequency of the galaxy that's enhanced by a factor of 4 to sort of emphasize the effect of the Coriolis force. And we just ran into the criticism again that this is not representative of the galaxy, but maybe going into the realm where we have enough compute power to actually have enough resolution to really push our Reynolds numbers and so on. But to some extent, these are still idealized simulations, I have to say. But yeah, so we can follow. We did 1-2 giga years for cases where we also were interested in actually studying the saturation. So this linear relation only holds ideally if the fields are so weak that the Lorentz force doesn't act back on the turbulence. As soon as the fields get strong enough that the Lorentz force becomes important, then actually topological constraints apply about magnetic helicity, and it can be shown that the alpha effect separates a helicity in small scales and large scales. So it's like when you wind a cable, actually do have a very long cable here, the omega loop, it turns out if you create the helicity on the large scales, you actually get a breadth on the small scales. And at some point, actually, this will physically sort of counteract. So the Lorentz forces, the field lines, they're resisting the motions. And so as soon as you go into equipartition, you have to account for these topological constraints. And in that case, you can determine the alpha effect as a function of the mean field strength, so the nonlinearity. And we attempted to do that. And there's a host of interesting physics on determining the quenching behavior with magnetic Reynolds number.
Okay, thanks. I have a couple other questions, but in the meantime, does anyone else have questions? I'm looking, I don't see anybody with a hand raised. Oh, Andrew has his hand up. Go ahead, Andrew.
Curious, and sorry if I missed this, but the Right. So the forcing by supernova strikes me as different from maybe the normal forcing from that I think about from hydrodynamic instabilities, in that it's very stochastic. So is that stochastic nature of the forcing? I didn't get if that was taken into account here, or how it affects things.
It is a very non-linear form of driving. So we essentially put 10 to 51 ergs in a single grid cell, and this creates a massive shock wave. And it is in a sense intermittent. So it's not delta correlated in time as your typical helical forcing a la Axel Brandenburg would be. So there are some aspects also that it's high Mach number. It doesn't dissipate like in a cascade. It shocks and so on. So, but all of this is essentially glossed over when you do the averages over an entire horizontal plane in your domain. And then it's really not about a turbulent cascade anymore, but it's more about means and fluctuations averaging out or not averaging out. So, and you do see these by chance fluctuations. So that's why we actually typically have very long baselines in time to get good results.
Yeah, I guess I'm also wondering if there's anything interesting about the, say, the time scale you get from the supernova rate, like how that time scale compares to the other time scales in the problem, whether it's rotational shear or other effects.
So they're typically like 2 per century. So this is rather short times. I was wondering whether the rotation scale you could discern from just the eddy turnover time. So the natural scale here is the eddy turnover time, but if Coriolis forces are important, then you should be able to pick out that time scale as well, I suppose. But we so far, we don't have enough statistics to actually go beyond these most basic kernels that would just be an exponential decay both in space and time.
All right, any other questions? Shuo, go ahead.
Yeah, I maybe I missed this point, but when I look at the field orientation in the galaxy plane, so I wonder how often can you see two parts of the gas run into each other with anti-parallel B fields? Have you ever estimate that? I mean, it's just a...
Yeah, that's a very interesting point, because the synchrotron polarization, it doesn't actually care about whether these fields are parallel or anti-parallel. So you could in principle say, okay, you just have magnetic fields that are on small scales, and they get sheared out by the differential rotation. And so you get just a sort of layers and layers of flux, but they can point in opposite directions, and they would still give a synchrotron signal, because the electron gyration, it doesn't care about the direction of the magnetic field, but only sort of
right. So for example, the polarization you see is one direction, but then you don't know whether the vector is pointing left or right.
That's right. Yeah. So what observers typically do to try and break this degeneracy is to actually also use Faraday rotation measure. So that's a rotation of the polarization plane by the magnetic field along the line of sight, and that is actually sensitive to the sign of the direction in which the magnetic field points. And so by that you can try to disentangle actually the large scale ordered field from the true large scale, from the sort of large scale. There were actually, I think various observers came up with 3 different terms for this, because it's actually quite involved already to talk about this. So this would be a large scale field that is anisotropic, and that wouldn't actually contribute to any net flux. Whereas what we actually create is really a flux in the galactic plane. But it's true, you can think of a component like that being overlaid. That wouldn't actually be captured in this mean field formalism.
Thank you.
All right, I think we are past time. I know we got started a little bit late. I don't see any other questions. I'll just make one quick announcement before we thank Oliver again, which is that I have just learned that maybe not everybody received the link to sign up to meet with Oliver. So it's coming around again. So if you, so keep an eye on your TAP mailing list emails for a link to his schedule. With that, I will just clap. And if anybody else wants to unmute and clap for Oliver again, thank you.